Good morning. We begin lecture 17 with a quick summary of what we have covered in lecture 16. I would like to take a substantial portion of today's lecture to answer a question that was raised by one of the students after the class. Again, definitely welcome questions of this nature. These actually are fairly deep questions, and so therefore we will take some time to answer it in its entirety. And I think the answer will become clearer as the course progresses, but I will try to make an attempt to give as complete an answer as possible. Today's goal is to look at one of the most fascinating examples that we have in wireless, that is taken from the opening pages of Say and Vishwanath, chapter 2, section 2.1. Definitely that is something that after today's lecture I would like you to go and read through in detail, because that gives you an amazing insight into the wireless channel. So let's begin with a quick summary of what we have been discussing in the last class. Been looking at the Rayleigh PDF. We spent quite a bit of time understanding Rayleigh PDF and its properties. The reason for that, it is one of the most commonly occurring channel types that we will encounter in non-line of sight wireless communications. We have the probability distribution function. We have also looked at the cumulative distribution function. It turns out that both of them give you very useful information, particularly from the point of view of understanding outage. CDF is a very, very good tool and an example. And we showed how we could relate the cumulative distribution function in terms of V by V RMS to the outage. And this also led us to finding a good way to deal with the margins that are needed in Rayleigh fading environments. I hope this concept is clear. This is something that we will definitely leverage going forward. Now, another element that I had encouraged you to look at is the shape of the PDF. And the reason for this is because of the different values that we computed in the last class. Let me just write that down. So VRMS is root 2 sigma, or 1.414 sigma, and the mean value V bar comes out to be 1.253 sigma, and the median value V50 comes out to be 1.177 sigma. Again, three values, you can see where approximately they lie. So if the VRMS is a very, very important parameter for us, because that sets the threshold of what you will see as the average received signal power. So keep in mind that that is going to be a very, very important parameter. The VRMS is going to tell us. So now if I have not kept any margin, the probability that I will run into fade is the probability that the V lies less than VRMS. This is VRMS. Notice that most of the larger values lie to the left of VRMS, which means the bulk of the probability is going to be there. So if I don't have any margin against fast fading, then the probability of outage pretty much is going to be the integral or the shaded portion here. Notice that's going to be a substantial part, and that is what we saw yesterday. Without margin, the probability of outage was, I think, 63%. Probability of outage was approximately 63%. Okay, now I want to introduce our notion of margin. I have introduced 10 dB of margin. 10 dB of margin says that I have shifted my average RMS value 10 dB above the nominal. So now the outage will be only much reduced. So this is the shift. This is the margin that I have introduced, and therefore the probability that I have an outage is still the amplitude less than this value is obtained by that integral. Okay, so again, I hope you are comfortable with this interpretations and where the margin comes in, how the margin plays a role in terms of improving the reliability in a fading environment. We move on. Next part is I wanted to look at BER. Again, this was something that we had discussed in the last class. Let me just quickly summarize the highlight. Probability of error of BPSK. We will use BPSK as our baseline, or BPSK or QPSK, because it's very useful to get the insights. But of course, the comments that we are making apply to all digital modulations that we have. So probability of error in BPSK in AWGN, result that you are familiar with, 2 times EB by N naught. And if we call this parameter as U, this is the complementary error function. So basically we are looking at a Gaussian, looking for this threshold U, and saying that anything, basically you are trying to get the integral in that region of the Gaussian, and therefore the natural way to interpret this result is that if I want the BER to decrease, my U should increase. So I should find ways to improve my signal to noise ratio. Okay, the more U increases, the BER is going to decrease. Now, how I am going to do that? I may do it by adding margin, increase the transmit power, increase the transmitter gain, whatever it is. Basically, it boils down to improving or increasing U. Now, the situation in the context of a fading environment, probability of error of BPSK in the context of fading with fading parameter, specific fading parameter alpha. This comes out to be, we saw in the last class, that this will be Q of alpha times square root of 2EB by N naught. And alpha has a tendency to be greater than 1 or less than 1, but the higher probability of being less than 1. So which means that your new SNR is going to shift to the left, so which means that you're going to have a larger, so this would be alpha times U, which would shift your and make your probability of error worse. So keep in mind that the bit error rate probability in a fading environment, BER in fading, has 2 dependencies. It has a dependency, it depends on, it is a function of EB by N naught, like all modulation schemes in AWGN. It is also a function of your the gain introduced by fading, and we call it gain, but invariably it is something that is going to reduce your signal level. Okay. Let's do a quick numerical example. Again, this is just to reinforce what we have said before. Supposing I had a nominal EB by N naught of 7 dB. The purpose of this example is twofold. One is to illustrate the principle. It's also useful for you to have a few data points in memory. Because if somebody were to tell you, I'm designing for you a BPSK system, I will design for you 10 power minus 4 BER at 0 dB EB by N naught, you say, okay, wait a minute, that's not possible. You must be able to have an intuitive feel for, okay, at what BER, at what SNR will I get a reasonable BER. So 2 things, keep the numbers also in mind. At a nominal value of 7 dB EB by N naught, you will get a bit error rate, which is given by Q of square root of 2 EB by N naught. This will be 10 power minus 3, and that's a very useful number to remember. 7 dB 10 power minus 3. It's a good checkpoint. Anytime somebody shows you a BR graph, just do a quick visual check, say, okay, this is correct. If it's something shifted to the right or to the left, you know that there is an error. So this is a good standard reference point. Now I am doing an experiment in fading channel. The first experiment, the SNR comes out to be 7 dB, alpha equal to 1, just by chance it came out to be that. The second experiment that I tried out, the SNR came out to be 4.3 dB. The BER, I plug it into the Q function, it comes out to be 10 power minus 2. You can check these values. You shouldn't say that I'm biased, trying to prove a point, taking all values below. Let's say that the experiment gave me 10 dB, the next trial. Very fair experiment. This is 5 into 10 power minus 5. Excellent BR performance, because that's a very steep portion of the graph. And then fourth one, really bad, 2 dB. 2 dB, 4 into 10 to the power of minus 2. Now you must repeat this at least 100 times and then take the average. I'm going to do a little shortcut. I'm going to take an average of these 4 values, assuming that I've done this experiment sufficient number of times. Nominal value of BER was 7 dB. Because of the fading parameter alpha, I got perturbations in my SNR. Somewhere lower, somewhere higher. Again, that's based on the Rayleigh statistics. Once I do this using the Rayleigh statistics properties and I do an average, but you have to do the average over a large number. In this particular example, the one I wanted to illustrate was that you got a BER of approximately 10 power minus 2. Okay. Why? Because there are a couple of problematic cases which are going to offset the good cases of BER, and they are going to dominate. So you notice that what was 10 power minus 3 in AWGN, again just as an illustrative example, suddenly became 10 power minus 2 in a fading environment. So that is what we highlighted in the class yesterday. The BER graphs that we are used to have a very steep fall. This is BER versus EB by N naught, because most of the time we have been working in a AWGN where the SNR is fixed. What you'll find in a fading environment is something that where the BER reduction as a function of SNR is very slow, and therefore we just need to keep that aspect in mind. Okay. Any questions on what we have covered so far? This is where we ended the last class. All the concepts clear? Okay. We move on now to answer the query that was raised yesterday. Again, I definitely want to commend you on asking this question. Again, feel free to ask these types of questions because they are what help the ability to understand the concepts that we are talking about. This is what we said yesterday. Base station to mobile station transmission system. It is a multipath transmission system. There is a standing wave pattern which creates peaks and troughs. Again, the picture I'm sure is very familiar in your mind. Now, these peaks and troughs are caused because of the phasor sum. Again, because of the way these phasors add constructively or destructively. Two things that they depend upon: one is the carrier frequency, and the other is the relative delays that come. If you take into account that they are coming not exactly at the same, but within the time resolvability window, there is some differences in their delays that contributes to it. Then we ask the question, what are the ways in which you can get out of a trough? You're in a bad situation, we can get out of a trough. So the options that we listed down yesterday were: move to a new location. One is you move. Second, you add FEC. And third, probably the most effective of the lot, was to do frequency hopping. Frequency hopping. Okay, so the question that was asked is this for CDMA systems as well? Okay, the very, very valid question. Let me just begin by saying whatever we had said yesterday was in the context of GSM. Okay, for frequency hopping is a very good method for GSM to get around of this the bad channel conditions. Now, it turns out that frequency is something that we do not do for CDMA. So the question is, then what do you do if you get stuck in a trough? Because a CDMA user is as likely to stand in this location as a GSM user. And probably the even more important question, what does the 4th generation systems do? Because they are OFDM, which are neither GSM nor CDMA, it is a different option. What are the ways in which we can handle that? Okay, so next few minutes is going to be addressing this, the answer to this question, because it requires 3 concepts to fully explain this one. The first one I want to address is the time resolvability issue. We did mention this. I thought I should highlight this a little bit more because it explains the answer to today's question. Yesterday we said that there is a parameter called time resolvability, and we said that usually it is given as delta tau. That basically tells you what is the resolution in the delay dimension that you can resolve. And I made a very generic statement that is inversely proportional to the bandwidth of the signal. let's be a little bit more precise and answer and explain this concept a little further. So let's take the GSM signal. So GSM signal uses a bit rate of 270.833 kilobits per second. Okay. Now, typically when you have a system that is using binary transmission, so this is a form of binary modulation. So the bandwidth required will be reciprocal of the bit rate. So the bandwidth required is approximately 1 over RB. But before that, just an incidental note, somebody asked me, one of the students asked after the class, why this really weird number, 270.833? Couldn't they have made it 271 or 270? That would have sounded much better. It turns out that a 13 megahertz crystal was easily available. Most of your receivers must have a frequency reference. So 13 megahertz, and dividing the frequency by an integer number turns out to be easier from a circuit implementation. So 13 megahertz by 48 is 270.833. So in case ever you are wondering why 270.833, it has nothing to do with what 270.833 looks like. It's a derivative of the 13 megahertz clock, and it was something that was found convenient in terms of the design system. Okay, now that's not important for us. The key point is this reciprocal, it's reciprocal, you didn't catch it, reciprocal of the T bit, not the RB. The bandwidth is proportional to RB. So this is proportional to 1 by TB or TS, T symbol. So the question that we have to ask is, what is T symbol or T bit? In our case, this is approximately 3.69 microseconds. 3.69 microseconds. Okay. So according to this course estimate, our time resolvability delta tau when I'm using GSM as my system of transmission is approximately the reciprocal, or basically it is of the order of 1 by TB, which is of the order of TB. Right? So approximately 3.69 microseconds, but it turns out with some very clever processing, we can reduce this to approximately 1/8 of a symbol. That is the time resolvability that we can achieve through the signal processing methods that we know. So this would be approximately 500 nanoseconds. Okay, so anything that arrives within a 500 nanosecond window, multipath components that arrive within a 500 nanoseconds window will look like the same for me. It cannot differentiate. So basically, if there is a multipath component that comes as 50 nanoseconds with a delay of 50 nanoseconds, and another multipath which comes with 100 nanoseconds, so maybe I draw it in this fashion. There are two multipath components which are approximately 50 nanoseconds apart. As far as when I do my processing with a GSM system, I cannot resolve, these two don't look like that. It looks like just one channel that is present, because I cannot resolve between these two multipath components. So you get a feel for what is the time resolution and what is the impact in terms of the system. Okay, now comes another very, very important principle, this notion of which parts arrive at the same time. So there again we go back to our analytical geometry, which says that if I have an ellipse and I have the foci, the path between the A to B, horrible straight line, okay. This path has the same distance as something like this or something like this. Okay? Anything which bounces, a single bounce of an ellipse will reach at the same time. So let's simplify matters. We're looking at those paths which arrive with a bounce. So now if I tell you what are those paths that will arrive at the same time, you will tell me those paths, this is the transmit antenna. This is the transmit antenna, this is the RX antenna. Between the two, the imaginary ellipse you draw, whichever bounces off and situated on the ellipse. Now, if you have this time resolution uncertainty, then it doesn't have to be on the ellipse. I cannot tell whether it's on the ellipse or whether it's inside this boundary. Notice it's no longer a line, it becomes an annular region. Basically it's a band around that. The greater the time resolution uncertainty, the wider this band is going to become, right? So that is a very, very important concept. So there is a term that describes those points that interact with the which create the multipath components. They are called the interacting objects. Interacting objects, sometimes shortened using the term IO, used quite often by Molish, but not so much in the other literature, but it's a correct term. It says that those objects that are creating this. Now let us look at what is the how does the channel look like for a system where there is time resolvability uncertainty. Okay, so here it is. You can think of it as several ellipses. Each of these ellipses has got a finite region around it, because anything that arrives with an interacting object in that location, I cannot tell the difference. So if I were to characterize my entire multipath for a system, though there is many different multipaths with finely varying multipath delays, if my time resolution is delta tau, it will look like everything between 0 and delta tau comes as, it looks like one path. Then between delta tau to 2 tau, 2 delta tau, another path. So basically this red corresponds to the portion from the innermost, all those from the innermost circle. The second one comes from the blue, the third one from the green and the yellow. Is that clear? So depending upon the bandwidth of the signal that I am working with, the number of paths are going to show up. Now if I have GSM with a time resolution of about 500 nanoseconds, and this entire spread that I have in terms of the multipath is only 200 nanoseconds, doesn't matter how many multipaths were there, it will look like a single multipath to me, because I cannot resolve between them. A very, very important concept. Basically the notion that you have interacting objects, you have the principle that if it is a single bounce, these have to be on an ellipse, and it is not just an ellipse, it is a annular region. Annular region, and the width of the annular region is wider. This region becomes wider if the bandwidth decreases. Why if bandwidth decreases? Bandwidth decreases, my time resolution becomes worse, so therefore I cannot tell the difference, the annular region becomes wider. Okay, so this is a very, very important notion for us to be able to understand and interpret, because this leads to the next concept, which we will refer to as the channel response. Channel response. Yesterday we said that the channel response is described by means of a two-dimensional function h of t comma tau. H of t comma tau. Now how will I characterize h of t comma tau? How many taps do I represent? Depends on my time resolvability, that will map according to this region. Now how does it make a difference, and how does it affect me in terms of my understanding of the wireless system? That is what is going to come next. So if there are any doubts, please feel free to raise it, because we are kind of building on that. So if I have a GSM signal, narrowband, compared to a 4G signal which has got 20 megahertz bandwidth. So the same channel looks like I have a few multipath components. The shape will look the same, but it looks like I just have a few multipath components. This is what it will look like for GSM. This is what it will look like for a 4G system. But basically you will have to sample it using a delta tau spacing. So for GSM it may look like this. It may look like this. For the 4G system may look very, very different. The same channel looks like you've got lots of multipath. Okay, you've got lots of multipath. So that's what we are trying to show. So the same channel looks different for a narrowband signal versus a broadband signal, all going back to the bandwidth resolvability. Okay, is that clear? So keep that picture in mind. So now comes the next part, which is the most critical in terms of the interpretation. So the true channel has got lots of multipath. So when I tell you that my filter has got a multipath like this, if I call this as h of t, I can tell you, please compute for me the frequency response, it will be h of f. When there's a lot of multipath, what you expect to see is that h of f will have lots of variations. Typical filter, right? It's got zeros, it's got poles. Basically, there is a lot of variations in the frequency response. This is h of f as a function of frequency. If I have only one tap in the time domain, frequency response is flat. So remember, we talked about flat fading versus frequency selective fading. This is flat, this is flat, this is frequency selective fading. This is very important for us to interpret the next slide. Okay, so now I have a channel which has got lots of multipath, and I have a certain frequency response that is given by the red signal. My GSM signal has got 200 kilohertz only. Therefore, its resolvability is very less. And let us assume it is such that the resolvability of a GSM multipath says there's only one tap. That's because of the resolvability. So the GSM channel sees a single tap channel, which means in the frequency response it is going to be flat. Am I right? And that is what we are showing here. The blue line is the GSM signal. That it only sees that, it looks like that portion of the based on the carrier frequency. If this is my carrier frequency, GSM will see a channel that looks very good, and it looks flat as far as the signal is concerned. It is easy for the GSM signal to detect the signal. Now, if your carrier frequency unfortunately had been located somewhere slightly differently, supposing if this had been your GSM location, unfortunately you will be in a fade. It is a flat channel as far as GSM is concerned, though the true channel has got a lot of variation. But to you it seems like a flat channel, and because you are sitting in a particular location where the channel response is bad, to you it looks like a bad channel which you cannot detect. So this is the scenario where we said frequency hop. Maybe you go from a bad channel to a good channel, you are happy, and then you keep doing that. Therefore, you don't get stuck in these bad channels, you come out of it. So why does frequency hopping work for GSM? Is that clear? Now, remember the CDMA system. CDMA system has a 5 megahertz bandwidth. So obviously it will see a different channel in terms of the time resolvability, because it's got much wider bandwidth and therefore much higher resolution. So as far as the CDMA is concerned, it says it's not a flat channel, definitely not. There is a lot of variation in the channel. So this is the bandwidth of the, this is the 5 megahertz signal, 5 megahertz, and what the CDMA signal says is, hey, it's not flat at all, there is a lot of variation. What is the variation? It says, oh, I can see several multipath components. They are sitting in different, slightly different delays, and they're actually arriving slightly staggered in time, and I'm able to see that. Now, what is the advantage that the CDMA system has that the GSM system does not have? The CDMA system can take these multipath components and align them in a co-phase manner and actually get a good signal to noise ratio out of it, because there are multipath components. If you co-phase the multipath components, it actually gives you ability. So in an intuitive way, is this portion of the signal bad, of the spectrum? It is bad for the CDMA system also. But there are enough good portions in the CDMA signal that I can actually detect the signal. That's an intuitive way of looking at it. The signal processing interpretation is that there were multipath components. If I didn't do anything, they will cancel each other. But if I can align all of them to become co-phased, then I can take advantage of that. This is what is done in a technique called the rake receiver. I'm sure you would have studied it in the context of CDMA, and that is why CDMA does not need to hop, provided you have sufficient bandwidth. Why? Because sufficient bandwidth means you can resolve enough multipath. You will take those multipath components and you will align them so that you can get a good signal to noise ratio and then be able to detect the signal. Any questions on this? Again, we have not yet talked about CDMA, but just the notion that it's a wideband signal, it has got better time resolution, and the receiver algorithm aligns the multipath components. As long as you are comfortable with those concepts, this is good. Okay, so GSM, frequency hopping, CDMA, rake receiver. Basically, you combine the multipath, you resolve the multipath and you combine. You don't need to do frequency hopping. It does not matter where you lie. As long as there are enough portions of good signal, you will recover your, you'll be able to detect the signal. Now, here comes the important question, what about OFDMA? It is not a spread spectrum signal. In fact, it is narrower than GSM. GSM is 200 kilohertz. Now, what is OFDM's bandwidth? Typically 10 kilohertz. So it will almost look like a line, or maybe as narrow as I can draw, 10 kilohertz. Now you say, well, what do? You obviously have to do frequency hopping, because there will be enough of these bad channels, right? There is a bad channel here, there is a bad channel here, so several of them. However, if you recall, OFDM is in the context of a wideband signal. Typically OFDM systems may be 20 megahertz wide. 20 megahertz wide. So there are large number of these narrowband carriers. Where do I hop? I cannot hop. I cannot hop all of them because I don't have enough spectrum to do hopping of a 20 megahertz signal. So what else can I do? What can I do? I cannot hop because it's a wideband signal. There are lots of these narrowband carriers which will be seeing flat channels, and many of them are going to be in bad conditions. What do? Equalization is needed if I am seeing a time dispersal channel, but if it's a flat fading channel, that means the time dispersion is not bothering me. It's basically it's a single tap channel. OFDM is very flexible, because those portions which have about, avoid using those carriers, because you've got enough other carriers which are good channels. So out of 1024, maybe 100 are bad channel conditions. You use the remaining ones. So you pick those subcarriers. Pick those subcarriers which are seeing good channel conditions with good SNR. Okay, that's it. SINR. It can not only be due to fading, it can also be that there is interference. You will pick those with good SINR. So whether it is a narrowband system, a wideband system like CDMA, which is doing spreading, or a wideband system which is constructed using a lot of narrowband carriers such as OFDM, all three of them, we have ways of handling the channel, but it goes back to our understanding of what the channel resolvability is and how do we deal with the channel resolvability issue. Okay? So this is to answer the question, frequency hopping, is it only for narrowband systems? The answer is yes. It is for narrowband systems, single carrier. Narrowband systems, multi-carrier, you just avoid using those bad channels. If it is a single carrier wideband system like CDMA, then you have time resolvability, you take advantage of the multipath and therefore are able to get a good performance in the channel. Any questions?
In yesterday's graph,
yeah,
the x-axis was position. Right?
Position.
Now you came to frequency.
Correct.
How did you
Okay, the question is, yesterday's class we were looking at a spatial distribution. So here is what we would, the way I would explain it. There is multipath occurring, and the multipath, when I look at it in a time perspective, there is multipath components that are arriving. Now that is one perspective. Now if I move from one position to another position, my multipath profile changes, the multipath components changes. So at each position that I am likely to find myself in, there is a channel impulse response that is present. It is dependent on where I am located in terms of the multipath components. It is dependent on the carrier frequency, because that's what tells me whether it's going to be in a trough or not. Now the multipath components that I see at my current location, multipath components, when I look at it in the frequency domain, there is a frequency response. And if that frequency response happens to be very bad at that point, it basically means that the phasors are adding in a destructive fashion. So that is why it corresponds to a null. So it is a physical location in the xy plane. At each location there is a set of multipath components that I receive, and the multipath components that I receive has got a certain frequency response, and depending upon my carrier frequency I may see this channel or this channel or this channel, depending if I was in GSM. The multipath components based on the location are fixed, but my carrier frequency can change. If I change my carrier frequency, the response of that particular multipath components to that carrier frequency changes. So that's what we are showing here. Okay, so you're right. There is a spatial distribution of peaks and troughs. Each position has a distribution of peaks and troughs in the frequency domain. For different frequencies there is a different gain, and so if you are unlucky to choose a frequency which had a bad frequency response, then you actually are affected in the, you can interpret, so you are giving an explanation both in the time as well as in the frequency. Let me move on. I would like to do a quick summary of the Rayleigh PDF. Maybe you should be helping me with that, but let me just in the interest of time, we are looking at it primarily in non-line of sight. This occurs in non-line of sight components. It also is a typical phenomenon when there is a large number of multipath. So the number of multipath components n is large and there is no dominant path. What happens when there is a dominant path we will be studying, but right now the assumption is that all of them are approximately of the similar power in terms of their strength, and this has been confirmed by a lot of measurements to verify that in practice something like Rayleigh fading actually occurs. So it has been validated through measurements. So there is no doubt about the usefulness of this model. Maybe an important question is, when is it not valid? Again, it's important to sort of say the negative side, saying that okay, you don't use it under these conditions. First and foremost, if there is a line of sight, it will the channel will not be Rayleigh statistics, it will not be there. Second, when you are in indoor environments, it may not have Rayleigh distribution. Why? Number of scatterers, because indoor there are not as many scatterers as you would have. The other one is ultra wideband systems. If I had there are modulation methods which will use 1 gigahertz bandwidth. Why wouldn't ultra wideband have Rayleigh fading? Ultra wideband has got extremely high time resolution. So it will say that at this delay only one path came. If only one path is there, there is no Rayleigh statistic. You must have averaging of a large number of paths. So ultra wideband systems have got very high time resolution, which actually changes the nature of the channel. So the other one is if you have very narrow beams. Remember we talked about sectorization. Sectorization typically is a 120 degrees, but you can also think of systems where you have very narrow beams. So if you have narrow beams, it does not match Rayleigh. Why? Again, number of scatterers, because you are limiting the scatterers that you will pick up. So therefore, and also remember we made the assumption that the scatterers are coming in all directions. Now when you have a narrow beam, it's very likely that your scatterers are in a particular angular section, not all around. So therefore again it will violate that. So there are it's something that you need to keep in mind. The impact of Rayleigh fading very critical for us, because in the way it affects the BER. It affects the BER and it affects it in a very significant manner. But the good thing about Rayleigh PDF is what characterizes a Rayleigh PDF? What parameter characterizes the Rayleigh PDF? VRMS. So basically, or sigma. Basically, there's only a single parameter that characterizes the Rayleigh PDF. Single parameter. you can think of it as sigma or as VRMS, both are equivalent. Once you specify sigma, the PDF is fully specified, and once that is given to you, you know the PDF, you know the CDF, you know the median value, everything gets fixed based on the description of sigma. So sigma is very critical for us, very important, and using that we use the ability to work with this. Okay, let me move on. Let me quickly mention something about the assignment number 2. Assignment number 2 more or less follows the discussion that we had in class yesterday. Keeping in mind that the fading environment is a multiplicative environment, it will affect your SNR, and the SNR will be affected by mod z squared, or if you think of alpha as the amplitude of the Rayleigh variable, Rayleigh random variable, then the modulus of z or alpha is what is going to affect me. So the experiment that you have been asked to do is the following. You've been asked to look at the theoretical BER of BPSK. BR versus EB by N naught. You've got a graph like this, and nominal value is here. Now about the nominal value, keeping that as your nominal value, you are asked to generate different values of alpha squared, EB by N naught. So basically you are represent alpha trial number, trial 1, trial 1, 2, like that, all the way up to 1,000 or 10,000, whatever you are asked to do. You generate enough of these alphas. For each of those alphas, according to the Rayleigh distribution, and what should be the value of sigma, because if I don't specify sigma, then it is not useful. So very important for us to answer this question. In the fading channel also, I want the average SNR to be the same as AWGN. So expected value of alpha squared EB by N naught, if I want it to be same as EB by N naught, which says that expected value of alpha squared must be equal to 1. Expected value of alpha squared is 2 sigma squared equal to 1. Okay, and what is sigma? Sigma is the variance of the Gaussian. So basically you must generate 2 Gaussians which have each one equal to sigma squared equal to 1/2. Okay, the X Gaussian has got variance 1/2, Y Gaussian has got variance 1/2. When I add them together, I will get a 2 sigma squared equal to 1. So basically I have to generate it in that fashion. If I generate it in that fashion, I am guaranteed that on average my average SNR in fading is going to be the same as the average SNR in AWGN. So now all the perturbations because of alpha, you can try, you will do the measurements. Remember the first example that we did, you will get several of these BERs, then you average it, and then you will find that your average is actually coming out to be the, so basically whatever we introduced at the start of this lecture is what we are going to be doing in computer experiment number 2. Now here is a important sort of question for you to think about and answer if you know what would be a reasonable explanation for this. So a student was told to simulate a modulation system in a fading environment and was told that AWGN has to be present, and AWGN is an additive impairment, and fading must also be introduced, Rayleigh fading, and this is a multiplicative impairment. And the student said, yes, I did this, and the result is BER in fading is equal to BER in AWGN. And says, I've checked it, 100% sure I have implemented fading, I have implemented AWGN, there is no difference in the BER. What happened?
He applied the fading after AWGN.
Okay, if he applies the fading after AWGN, let me take a quick look at it. So this is the transmitter, added the noise AWGN. So that means you have a certain EB by N naught that is happening here, or in other words there is signal coming in, noise coming in, and this is the multiplicative factor alpha. It is multiplying the signal and the noise. So the resultant SNR at this point is EB by N naught, because it multiplied the noise also, and therefore at the receiver did not find any difference in the BER performance because the noise also got scaled. But keep in mind, where does fading occur? Fading occurs in the channel. So fading occurs in the channel, this occurs in the receiver. We cannot interchange the two. Please never be tempted to do that, because you will get the wrong answer. The fading affects your signal. Noise gets added regardless of what your signal level is, and therefore that is why the fading becomes a problem. So again, you got it right away. It is because the student was correct. They had implemented fading and AWGN, but if you implement it in the wrong order, you get the wrong conclusion. We just have a few minutes. Let me just introduce the next topic that we would like to study. This is an example from Say and Vishwanath, section 2.1.1. Again, please do read that. Let me section 2.1.1. Let me just introduce the problem statement to you. This is one of the most classic examples that we encounter in wireless communications. One of the most simple examples, but gives you almost all the necessary understanding of wireless. And again, that's the beauty of this example. So some basics. In electromagnetic fields, we have an electric field and a magnetic field. And the direction of the electric and magnetic field, I don't know, you have a right hand rule and all, E cross B. So both of them are perpendicular to the line of transmission. So keep that in mind. E field is perpendicular to the direction of propagation, and E and B can be related to each other. So we always more or less look at only the understanding with respect to the E field. Now E field has dependencies on the following functions. Let us say that you have a transmitter in free space. The electric field that is generated by this transmitter in free space is a function of F, the frequency, the carrier frequency, or maybe call it as FC. The time that has elapsed, basically there is a dependence on time, and there is a dependence on the displacement. So basically, if I have a transmitting antenna, I can think about electric field in different locations, and I can then characterize it in that fashion. Okay. Now the displacement U is a function of three parameters. It's a function of the distance r. It's a function of the angle in the azimuthal plane. It is a angle in terms of the elevation angle. So again, this is a diagram that we have drawn previously. So if I were to look at a point in three-dimensional space, okay, this is the displacement r. The angle with respect to the azimuth is theta. The angle with respect to the horizontal is the elevation angle, that is phi. Using this, we can you can pin down the position. So I have a radiating element that has the radiation depends on the carrier frequency and the function of time, and depending upon where I am situated, I will get a certain intensity of radiation. So the transmitted signal, so basically we will call that as E transmitted. It will be a function of the carrier frequency, of time, and of the displacement. Again, it's a simplified example, so keep that picture in mind. There is a gain term, alpha, and that depends on the antenna gain and all of those parameters. So there is a gain term. The electric field decays in free space reciprocal to the distance that you have traversed. So it is that gain, whatever is there initially, will decay as a function as 1 by r, and the rest of the dependence, it is basically a sinusoidal function cosine 2 pi fc t, and how much distance have you traversed? It is r divided by c, the speed of light. That tells you how much time lag has occurred. So if I am sitting at a distance r at a particular location in three-dimensional space, the received signal strength can be described by a gain term and a reciprocal of 1 by r and times cosine 2 pi fct. It's 2 pi fct at the transmitter. By the time it reaches me, there is a slight lag. So that is the lag that is described here. Again, this is something that we have seen before. The reason I introduce it using the notation of Say and Vishwanath is that it will enable you to understand. So why is this r by c important? R is the displacement. This is the displacement or the distance, and c is the velocity of light. So that's the time that it takes for the electromagnetic wave to reach you at the receiver location. So velocity of light. Okay. So now the next step is I am going to write the received electrical vector. Nothing changes here except that I may have a receive antenna gain. So basically it will be depend on carrier frequency, it's a function of time, it's a function of the displacement I am at that location. I'll just make it as alpha by r, whatever is the gain of the transmitter added to the gain of the receiver, and it is cosine 2 pi fc t minus r by c. This is the electric field that is received by me. It's a simplified model. It assumes that it is free space propagation. The electric field decays inversely as a function of the radius, and so this is the basic formulation. You may say nothing you can gain out of this. There is nothing new in this formulation, but the beauty of it is using this, Say and Vishwanath have constructed one of the most elegant examples to explain all of the concepts that are in wireless. Things that we took quite a bit of effort. Remember we derived all these multipath components, Doppler shift, and everything. Everything comes in very, very simple, elegant fashion. We will cover that in tomorrow's class. Thank you.